All right. Last time we left off right here, and we were talking about solving quadratics with that zero property rule. And so that's what we're going to be I want to just review over this a little bit at the beginning class, a couple of these, and just make sure that we're all on the same page and remember what to do on this. So let's look at part D, right? In order to solve this, it's usually we need to get it into this form like A is over here, where we have everything on one side and the other side's equal to 0. And if there's any parentheses, we've got to clear those parentheses and put any of our like terms together. So on this one, we'd want to distribute that 6x through, so that will give us 6x squared, 6x times x, and then 6x times 1 would just give us 6x, and then plus x equals 5. And so we need to get our x terms together. So 6x squared plus, we got 6x plus a 1x, so that's 7x. And then remember, we need to get this other side equal to 0, so that means we're going to end up subtracting the 5 over to the left-hand side. All right, so that we get 0 over here. And then from here, we're trying to look and see if we can factor that, and if we can factor it, how it would factor. So I want to give you just a minute to try and factor that. Remember, our leading coefficient, right, is not 1, so you can't go straight to our factoring. You've got to make it into a 4-term polynomial, or do the factor, the synthetic factoring, or something like that. Okay, so let me give you a minute, see what you can do with that one, factor that one out. Okay, when you think you have your answer, raise your hand so I can see where everybody's at. All right, only a couple of you have your hands up, so let's see. Can't tell if some of you are stuck or whatever. Make sure, speak up if you're not quite sure what to do, because I can't see what you guys are doing or, where you're getting stuck and stuff, so I'm relying on you to speak up. And remember, somebody else in the class probably is stuck in the same spot, so you're going to be helping out a lot of people if you speak up. All right, so maybe at this point we need to look and see. We're trying to figure out what multiplies to be negative 30, because remember we need to multiply that first term along with that last term, right, including that negative with that 5. So 6 times negative 5 gives us negative 30. And then you're needing to list out, what things multiply to be negative 30. Well, we know that one of them has to be a positive and one of them has to be a negative. And so you could list all those out, but it might just be easiest to just, just to list out things in order. So meaning I'm going to go and say, okay, I know 1 times 30 is 30, and maybe I'll just put my negative with that the first number. I also know that 2 times 15 is 30, so I'll just say negative 2 times 15. All right, negative 3 times 10. And 4 times something, there's not anything. 5 times 6. All right, but remember, one of them has to be negative. It might not necessarily be this one that I made negative. So I'm trying to think to myself, is there any way that I could combine these together, right, that they would add to be 7? Well, on this one, it does happen to be this one, right, negative 3 and positive 10. So notice how I just worked through things in an organized manner to help me figure out which factors I want on that. So if I do negative 3 times 10, that gives me negative 30. If I do negative 3 plus 10, I get 7. So those are what I want. So if I make it into a 4-term polynomial, that 6x squared is going to stay the same. Remember, 7x we're going to change to be that negative 3x plus 10x. All right, I was trying to do that. And it doesn't matter which order you put these in. If you put, 10x minus 3x, that doesn't matter. In the end, when you do this, it will all come out to be the same. So I have had that question before where students are like, I'm not sure which one I need to put first and which one I need to put second. And it doesn't matter, okay? So these are our 4 terms. So from there we could do the factor by grouping, you could do the box method, you could do, synthetic factoring from there. I'm going to go and do the box method, but you pick which way is working best for your brain to do this. All right, so I'll have my 6x squared in one box, then negative 3x, then positive 10x, and then negative 5. And so remember, I'm looking on my rows and on my columns, and I'm just pulling out the greatest common factor on those things. So if I start on this top row, right, I can see that I have a 3 and an x that could be pulled out of both of those. Okay. On the bottom, I can see that 5 divides into both of those, so 5 could come out. Right, and then if I look on my columns, well, 6 and 10, greatest common factor of those is 2, but then there's also an x I can take out, so that'd be a 2x. And then on this one, this one gets a little bit tricky sometimes for some people to see on this, but there's only a 1 that could come out on this, but since this top term is negative, we're actually going to want to factor out a negative 1 there, right? And so when I do that, let's see here, let me make sure so the answer on that, when we factor it, would be 3x plus 5 times 2x minus 1. And then maybe if we look at it, one of the other ways, maybe some of you are thinking, okay, I want to do that synthetic factoring. Let me do that in a different color so we can kind of keep straight what we're doing here. So if I have the synthetic factoring, I take my numbers, my negative 3 and my positive 10, and those are the denominators on a fraction. And then whatever my leading coefficient is, right, is going to be my top number here. And these are my x's. And then I'm looking to see if I could reduce these fractions, right? And so this can be reduced. And notice it's important that I keep that negative with that 3 there, because that's going to help me write out my factors correctly. So if I reduce this, well, 2 will divide into both of those. And so that, let me see, let me change it here. So I'll go into that once, and into this twice. So that means that this fraction will be written as the factor 2x minus 1, which matches this other one that we did the other way, right? And then if I look at my other fractions, 2 will divide into both of those, right? And that will leave me, I've got my 3x on the top, and it's a positive 5 on the bottom, so plus 5. So either way you do this, you still would come up with those answers, but we're not quite done yet. Those are just the factorings of it, right? This is how we can factor these. But it actually wants us to solve this, right? So we've got to take it one step further once we know what the factors are. Then we're going to set those equal to 0 and solve it. So to solve this, right, we'll have 3x plus 5, and then 2x minus 1. And we put those equal to 0, so that means we have to put each part equal to 0. So 3x plus 5 equals 0, and 2x minus 1 equals 0. And then solve for x there. So that will give us 3x equals negative 5. Divide by 3, x equals negative 5/3. All right, and then same thing over here. Let's add 1 over, and then we'll divide by 2. So x is 1/2. So those would be the two answers that we get. And remember, when we find these are our x-intercepts, is what we just found. Or we also call them zeros in math. So what questions can I answer on that one? I know that one kind of had a lot to it, but I wanted to make sure we went back and talked about, just quickly reviewed over what we did last time. What questions can I answer for you there? Remember, speak up if you have a question. You know, it's going to be helping other people too.
So is there a method that, like, this would have been easiest to solve, or is it really just what works best, like what you understand the most?
You mean the method of factoring it, or? Yeah, it doesn't really matter. I mean, I always think that the synthetic factoring is the fastest way, but some people just, they don't like that way, and so they'd prefer to use the box method instead. So yeah, so I would just say it probably just depends on, it's more just preference more than anything in getting that factored.
Okay, thank you.
Yeah, is everybody understanding how we did factoring, at least some way? Like, whether or not you used the box method or synthetic factoring, maybe used factor by grouping. Raise your hands if you feel like you understand how to do this type of factoring. Let's see.
Is there any way you can do another one with the box method?
Yeah, we definitely can. We'll do a lot of things with factoring, so you bet.
Will we be doing problem E?
I'm going to skip down and probably do F instead, but we could do E. Why don't we do E really quick? Because the factoring of that's a little bit different. Did you have a question about that?
Yeah, there were a couple problems on one of the 7.2 homeworks that I just didn't know how to do, and it was about that same problem.
Okay, yeah, let's look at this. So this is, notice that we have a perfect square, right, in both of these places. So this is a difference of squares like we talked about last time. So noticing that, and that they're connected by a subtract sign, you're going to be able to use that. Maybe I'll just write it over here. So if you have a squared minus b squared, right? So something squared minus something squared, that's going to factor to be a plus b times a minus b. But, and one thing that we didn't talk about last time, but I want to make sure we bring up today, is if we have a squared plus b squared, this can't ever be factored. It can't. And so we call that prime. So if there's a plus sign in between, those can't be factored. Like if we looked at something like, I'll just do something maybe a little bit, oops, I didn't really want that on the outside there, but if I just have x squared plus 4 and I'm trying to factor that, right, then we'd say, okay, x times x is my x squared, but then I'm thinking what times what is 4 that adds to be 0? And there's no possible thing that we can come up with for that, because, you know, to get 4 we have 1 times 4 or 2 times 2. We could also have negatives, -1 times -4 or -2 times -2, but none of these will add up to be 0. And so there's no possible way to be able to do that, okay? So I just want to make sure that's clear. If it's connected by a plus sign, don't have to do anything, you just write it's prime, because it cannot be factored. But on this one we have a subtract sign. So we want to, let me kind of put a little box around this so we know that's not part of this one. But I want to change this and I want to rewrite it so it looks like this. Something all squared minus something all squared. All right, so if I'm looking here on my 64x squared, right, I'm trying to think of what times what would give me 64x squared. And for some students it's just easier to break it down by, you know, the number first. So what times what is 64? Well, that would be 8. And then what times what gives me x squared? Well, that would be x. All right, because if I did 8x times 8x, that would be 64x squared. Right? But I need to write it like this so I know that that 8x is my a. Right, that I'm dealing with here and in this. Right, and then on my second parenthesis, I'm thinking what times what gives me 9? Well, that will be 3. Right. And so then I, that's going to be my b. So my a is 8x and my b is 3. And then I'm just going to be using this kind of formula of sorts to put this in. Right? So when I factor that, I'm going to say, okay, in my first parenthesis, right, I'm going to have my a plus b, so that would be 8x plus 3. And then in my second parenthesis, I need my a minus b. So my a minus b would be 8x minus 3. And so that would be my answer in factored form, right? This is what I have as factoring. It's not my answer quite yet, but I want to make sure that that's clear that you see. But if you wanted to check and make sure you factored that right, you can always FOIL it back through, and then you'll come back with what you started with up here. Okay. All right, so let me stop right there a second before we solve the rest of this the rest of the way. What questions do you have on the factoring of this type of problem? If you have one, just speak up. Just unmic yourself and ask.
I just think for me, like, sometimes I just get confused about the negatives, like, especially with like other problems with 3 variables, if there's like a plus and a negative.
Mm-hmm.
Like plus plus, it's all going to be positive, but like if the negative's in the front or in the back, I just get confused on where
Yeah, and so that's why sometimes it's just a good idea to try and, FOIL it back out and see if you have it correct while you're kind of, getting used to the factoring and stuff like that. And really, a lot of that, it really just comes with practice with factoring. The more you do it, the I don't know, the easier I guess it becomes, just because you get more used to it. But yeah, I agree. And especially with those sum and differences of cubes, those are kind of long, right? Those equations, and so that makes it a little bit difficult to kind of do. But try and when you're doing your homework, try not to look at it, and see if you have it down or not, or before you do a problem, maybe write it out, like what that's supposed to look like before you do the problem, just so you can be practicing, for kind of testing situations. So, all right, so after you do these, right, then we're going to set both parts equal to 0 and solve it, because it's still, on this, it's asking us to solve this, not just factor it. And that's the other thing that I want to make sure is clear on your homework. Make sure you're looking for the directions. Is it saying just to factor, or is it asking you to solve it? And if it's asking you to solve it, then you need to set it equal to 0, which means you're going to take both factors and set each of those equal to 0 to find your answer, to figure out what x is. All right, so here we get -3/8, right? And then pretty similarly, maybe, you can see we're going to get +3/8 for the other one. Okay. So those would be our answers on that. All right, but you got to get it factored first. Got to figure out, okay, how can I do this factoring here? So factoring really is just a nice tool that we have in math to help make things maybe a little bit easier for us to solve different types of problems. Okay, let's look at this. Let's look at F also. Okay, and I want somebody to tell me, what do you think you would do first on this? Go ahead and just speak up. You know.
Would you subtract 18x to make it equal to 0?
Exactly. Yeah. So whenever you see an x squared in something that you're trying to solve, you got to think, okay, I'm going to try and get everything over to one side so the other side can be equal to 0. Awesome. All right, so let's do that. So if I subtract the 18x over, then I get 14x squared minus 18x equals 0. Okay, now what can I do from here? Anybody have an idea? Do you guys see any greatest common factors? Okay, so you always look for GCF, right? So you always want to do this. Whenever we're factoring, try and see, is there a greatest common factor that can come out of both of those? And on this one there is. Looks like 2 can come out of both our 14 and 18. And by come out, I mean divide out, right? We're thinking what divides in, what's the biggest number that divides into both 14 and 18? So 2 does. And then I also see that I have an x that can divide out also. All right, and then so what I'm really doing is dividing each of those parts by 2x. And then in the parenthesis, I'm just going to have my leftovers. So 14x squared divided by 2x will give me 7x, and negative 18x divided by 2x will give me minus 9. All right, and then equals 0. So I'm still going, right? You've got to factor it. And now we're going to set both parts equal to 0. So I have 2x equals 0 and 7x minus 9 equals 0. And then if I divide by 2, well, it doesn't matter. 0 divided by anything is still just 0. And then here I'll add 9 over and divide by 7. So x is 9/7. So those would be my two answers. Okay, and again, these are my x-intercepts. If I was to graph it, these would be the x-intercepts. Okay, I want to make sure that's clear. What is it that we're finding? Why are we doing this? Well, these are parts of the parabola that are important parts that help us to graph it easily. Okay, questions on that one? You guys are so quiet. It's just so eerily quiet. Next week I'm going to try out a different thing where I'm going to try and get you guys into some groups. And so we're going to try that out and see how that goes on here. Still trying to play around with that and get that figured out. But so it might be a little bit, I don't know. We'll see how it goes next time. All right, was there somebody that had a question though? Go ahead and speak up if you did. Okay, well, let's move on to 7.4, and we're still going to be using all of these methods that we talked about in this. So we could still, use the box method or the factor by grouping or the synthetic factoring. And remember, we want to use those when the leading coefficient is not 1. Right? So on this one, we don't need to really use those methods because our leading coefficient is already 1. But what I want you to do on this first is we're going to now practice, using our tools that we have, right, with factoring, and we're going to factor this first, and then we'll do some stuff with it. Okay, so this f of x equals x squared plus 5x plus 6. Right, also could be written as, if I factored it, right, x times x gives me my x squared. What times what is 6 that adds to be 5? And that would be 3, positive 3, and positive 2. Right, and so this would be our factored form of this. So what I want you to do on this is we're going to, again, kind of go back to what we talked about before, where we said, okay, there's certain x's that would be best to choose on this to make our graph, to make it easier for us. So we said we'd want to, after it's in factored form, we want to know, okay, what numbers make those go to 0, right? Because that's going to be our x-intercepts like we talked about before. So let's see. So remember, we want to find the x-intercepts. We also want to know what the y-intercept is, and we want to know what the vertex is. So if we know those 4 points of our graph, it's going to be a lot easier to graph this. So we're going to pick our x's in a smart way, right? Kind of like we talked about at the beginning of this in 7.1. So somebody tell me, just unmute yourself and tell me what would a good x be to choose on this.
-3.
Okay, why -3?
If you put it in for x, then it equals to 0.
Yeah, so it makes that first factor go to 0. So that would be a good one. Okay, somebody else tell me another x. What would another good x be to pick?
-2.
-2 would be another good one. Why is that one good, Michael?
Just because that, if you plug it into x, it goes to 0.
Yeah, it makes this other one go to 0. Awesome. Okay, so that would be a good one. pick there. Okay, what other ones would be good to pick? 0. Yep, 0 would be good because 0 is going to be, that would give us our y-intercept. Remember to find our y-intercept. We let x equal 0 and solve for y. Okay, and then how do we find our vertex? Remember how we pick the x to find our vertex? We got to pick halfway in between our two x-intercepts. And so, you know, sometimes that point isn't going to be a whole number all the time. But remember we said we'd add those two together. So -3 plus -2 divided by 2. So -5 divided by 2 is going to be -2.5. Right? So that would be another one we want to pick. And we want to know our vertex because that's a very important part of our parabola. That's that turnaround point. And, you know, even with all of the stuff that maybe you've been seeing with the coronavirus and stuff like that, a lot of these are, you know, it's kind of like an exponential growth going up, and then it kind of flattens out. And sometimes you hear them call that, you know, the apex of it. But it's also, it's the vertex of this. It's that turnaround point when it's going to be coming back down. So it's a very important part of the parabola that we always want to know. Okay, so now we have our x's, and we're going to put those in here in place of x to figure it out. So, right, so in our first one we'll have -3 plus 3, and then -3 plus 2. Well, we know that that's 0, right? And 0 times anything is still going to give us 0, right? So one of my points is -3, 0. So that looks like about here, perhaps, on our graph. Right? And then same thing kind of happens with -2 here. If I put -2 in place of my x, and some of you are going to get to the point where you're not going to have to put this in all the time, but I just want to make sure you're seeing why it's happening, right? 0 times anything is just 0. So -2, 0 is another point. All right, and then if I put 0 in place of my x's, I get 0 plus 3 times 0 plus 2. So 0 plus 3 is 3. I got 2 there. So that gives me 6. So another point is 0, 6. So that would be, let's see, over 0 of 6. What's happening here? Did I do that right? Okay. I don't have a negative or anything, right? Okay. And so then I can see kind of what the shape of my parabola is kind of looking like here. It's going to be, remember, these are my x-intercepts, and since it doesn't have like a negative out in front, I know it's going to be a right side up parabola. Okay, but let's figure out where that vertex is. Remember, I know it's going to be halfway in between my two x-intercepts. So if I put the -2.5 in place of my x, all right, I get -2.5, oops, plus 3, and then in my other parenthesis, -2.5 plus 2. Well, -2.5 plus 3 is just going to give me a positive 0.5. Let me try and then on this one, -2.3 plus 2 would be a -0.5. And a -0.5 times a positive 0.5 times a -0.5 gives me a -0.25. All right, so that's a pretty small number. So let's see, so my ordered pair is -2.5, comma, -0.25. All right, so I'm going to the left negative 2.5, and then down just, and that's a quarter, right? So not very far, so maybe about there. Right. And then the other thing that I wanted to talk about that we talked about a little bit before was the axis of symmetry. Right? So the axis of symmetry with any parabola, these parabolas are always symmetric, meaning if you were to, fold them over on the line of symmetry, that they would land on top of each other, right? And so our line of symmetry always lines up with our vertex. It always goes through that vertex. This is not the easiest to try and draw on here. See if I can do that. Okay, so there's my axis of symmetry. And that would be the line x equals, right, our negative 2.5. That's what the line is called, that dotted line that I put in there. And sometimes it'll ask you what that axis of symmetry is, and it always corresponds with the x value of our vertex. Okay? And then remember I said there's always going to be, like since it's symmetric, like you can see that this point and this point are symmetrical to each other. Well, that means that this y-intercept up here also has a point that's going to be symmetrical to it. So it looks like it's about 1.5 that way, so about 1.5 this way would be where our other point would be. And so then we can kind of just make our sketch of our parabola. Whoa. Okay. And then going the other way up like this. All right, something like that. But remember that the bottom of a parabola is always a U-shaped. It's not a V, that's a different type of graph. So make sure it's not, your graphs aren't coming down at a point, but they're always going to be U-shaped. Okay. All right, what questions can I answer about that one on how to graph that? Does everybody understand how we found these x's? There was a few people that responded and knew how to find those, but what can I clarify there?
Can you go over how you found the vertex again?
Yeah, so the vertex is always going to be halfway between our x-intercepts. So that's what I did right down here. So I took my -3 and my -2, and I found the average between them. So -3 plus -2 all divided by 2, because the average of them, right, is going to put it smack dab in the middle. If I have -2 and -3, -2.5 is right in the middle of those two. But sometimes it was hard for some students when it's sometimes it's a little bit more difficult to figure out where that's going to be. So I'm just saying you can always do this, find the average, right, of the x-intercepts. Okay, and that's going to give you that point there. Good question, because that one is a tricky one to figure out sometimes.
Okay, thank you.
You're welcome. Anything else on there? All right, well, let's try this one then. So you are going to need to graph this one, and you're going to need to factor it first. But when the leading coefficient is negative, and maybe I'll write this out here, right? So that -1, right? Do you see that -1 there? It needs to be factored out first. Okay, so if there is a negative there, we're going to factor that out. Okay, so when I do that, I I get. So when I pull out my -1, right, and that means I'm dividing each of those by -1, that will leave me a positive x squared, and then a plus 4x, and then a minus 12. I'm basically just switching all of those terms to the opposite. But the reason we want to do that is it's going to make the factoring of this next part easier if that leading term is still positive, okay? But we still need to keep that negative out in front. Okay, and then we don't have another number. We don't have to do the box method or anything like that on this because the leading coefficient is 1 there, right? But let's look at this and see what times what is -12 that adds to be 4. Anybody tell me what you think of there? What times what is -12 that would add to be positive 4?
6 and -2.
Yeah, so positive 6
Yes.
and -2. All right, because we want it to end up being a positive 4. Awesome, thank you. Okay, and now this is the formula that we're going to be using, right, on this, and it's going to help us pick our x's. So let me give you a minute, and I want you guys to, figure out what x's you should pick, right, so that you can find the x-intercepts, right, both of them, the y-intercept, and the vertex, or maybe I'll put the vertex first. So remember that's the halfway between x-intercepts. Okay. And then the last one would be the y-intercept. Okay, so try and pick the x's that you think would be best for this one. Okay, so hopefully you picked -6, 2, -2, and 0. All right, and then when you're putting these in, just make sure you don't forget about that -1 that's now on the outside, right? So on this one you're doing -1 times, -6 plus 6, and then -6 minus 2. But again, when 0 is multiplied by anything, right, we're just going to get 0 for that answer there. Did somebody have a question? Tell if it. Somebody just came into the class. I heard a little beep, but it's the same sound if you come into the class or if you're raising your hand. So, okay, so try these other ones also, and then try and see what your graph would look like from this. All right, when you get done with yours, take a look at what I came up with. Make sure, see if you came up with those same points. Or if you came up with something different, check and see, was it just like a negative mistake or something like that? And then check the graph. And what would the name of our axis of symmetry be on this one? What is the name of this line right here, this axis of symmetry?
X equals -2?
Yeah, x equals -2. Remember when we have an x equals some number, that's a vertical line, right? And that's what we want for these axes of the axis of symmetry. And it's going through at -2. Remember, you can also find that because it's the x of your vertex, right? The x coordinate of your vertex. So we'll always go through that point. All right. Having such a hard time reading, you guys. It's so crazy. Cannot see your faces. Only a few of you are interacting with me, so I cannot tell what's going on. So I might have to just start calling on some of you randomly.
I do have a question.
Okay.
So we would totally forget about the -1 when we're trying to find our x-intercepts until we try to find the y, right?
Say that one more time. What do you mean?
So with our factoring, there's the -1 out in front, so we wouldn't do anything with the -1 to find our x-intercept until we try to find the y.
Still not sure what you're saying. Do you mean like these x's that you're picking, or?
So we wouldn't use the -1 to find the x, right?
No. Oh, okay, I see what you mean, because, yeah, there's no x on that part. If it said like x minus 1, right, as a factor, then we would use that part. But yeah, this is just going to be a number out in front that we're going to be multiplying by both of those, but you're only looking at the ones that have, the factors that have the x's in them. Does that make sense?
Yeah, a lot more things.
Okay, yeah, thanks for asking that. That's good. Other questions on that? All right, let's go look at this one now. Okay, now on this one, you might need to have a little bit of space to do your factoring, maybe, you know, up in here or something, because this one isn't going to be as easy to factor because it has a leading coefficient, right, of 4, not a leading coefficient of 1. So I want you guys to try and do the factoring for that over here first. Okay, so let's factor that. Whichever way you've been thinking. I'm going to try the box method or synthetic factoring. Give you a minute, because this type of factoring you've got to know how to do. If you're stuck somewhere, you need to ask. All right, Mickey, you have a question?
Sorry.
No, you're good.
Where's the multiplying? Where did you get the 28? I'm sorry, I'm lost a little bit.
Because you always have to, whenever the leading coefficient is at 1, you have to take that first number and multiply it by the last number.
Oh, the 4 and the 7. Okay, got it. Okay.
Yep.
Thank you.
Yep. See, Rachel, did you have another one, or was that from before? You can just put...
Before, sorry.
Oh, okay, no worries. Just want to make sure I'm not overlooking anybody's questions. Okay, let's see where you guys are at, right? So we did 4 times 7 equals 28. So what multiplies to be 28? That adds to be 16. And so if you list out all the possibilities of what times what is 28, we find that 14 and 2, positive 14 and 2, multiply to be 28, add to be 16. So those are what we want to put, right, when we're breaking down the 16x. We'll break it down to 14x plus 2x. And then someone wanted to go through, I think it was Brandon, wanted to go through the box method again, which I think is a really good idea. So let's look at this, right? So if we're, again, you're trying to find the greatest common factor. What is the biggest thing that divides into the numbers in each row and in each column? So in this top row, right, 2 will divide into both of those. And there's also an x, right, that can divide into those. So 2x would be that part. Is everybody okay with that? Seeing that that's the greatest common factor there. And then on the bottom row, right, looks like there's nothing, but remember there's always 1. If it looks like there's nothing, there's still a 1 that could be divided there. So 1. And then if we look at our columns, right, so let's look at this first column first, right, so it looks like the largest number that will divide into both of those is 2, and there's also an x that can be divided out, so 2x. And then on that other column, 7 can divide into both of those. It's the greatest common factor there. And these were both positive, so have that. So that means that it's going to factor to be 2x plus 7 in one parenthesis and 2x plus 1 in the other parenthesis. Right? And if you didn't do it by the box method, like I said, I'm not saying that you have to do it this way, but make sure that you came up with this overall, right? Because that's how we're going to rewrite this now. So we want to rewrite this as the 2x plus 7 times the 2x plus 1. And now our x's this time that we're picking, for our x-intercepts and stuff like that, look like, it's not going to be as easy maybe as the other ones. But remember, to figure out what those are, you're really just setting each of those equal to 0. So you're doing, 2x plus 7 equals 0. And so like minus the 7 over and then divide by 2. Right? And so negative 7/2 is going to be one of the ones that I want. And if you want to change that to a decimal instead, I'm totally fine with that. That would be negative 3.5. All right, it's up to you. Some people like working with fractions, other people like working with decimals. It doesn't matter to me. Just to make sure that it's something that works for you. And then what about this other one? when we set this part equal to 0 and solve, what do we get here? Because this is going to tell us another x we want.
-1/2?
Yeah, -1/2. Right, so -1/2, or if you want to write it as -0.5, like I said, if you'd rather write it as a decimal, I'm perfectly fine with that. Okay, and then, so these are going to be our x-intercepts, right? That's what we found with these. That's why we're choosing those x's specifically. And then we want to figure out, let's do our vertex next, remember, which is our halfway between the x-intercepts. Okay, so what would that be, or how could we find that? What do we want there?
Don't we add those and then divide them by 2?
Yeah, so let's do -3.5 plus -0.5, right, all divided by 2. So that's really going to be a -4 divided by 2. So that works out a little bit nicer, right? So -2 is what we want to put in place of our x here. That's halfway between those guys. And then to find our y-intercept, we'll always choose 0 to be our x. All right, so I want you to take it from here, and I want you to graph that on the, like, figure out what your y's are going to end up being, so you can find those ordered pairs, and then graph it on the grid here. Make sure you say what the line of symmetry is also. Nikki.
This might be a silly question, but I don't know if anybody else feels this way. Is there like a virtual study group that we could like form within our class or something? Because that's where I really learn.
Yeah, I know. And that's why next time I'm going to try and do like something where we can break out into groups and stuff, because I know people just don't feel comfortable speaking up, like as a, like as a whole class. I wish you guys felt a little bit more comfortable doing that. But yeah, so I'm going to try and do that next time, where we're going to be working in study groups. But on Monday, I wanted to try and do, well, I'm going to be assigning you a lab to do, but I wanted to find a time when you guys could kind of come together and meet, to kind of work on that lab a little bit together before class and stuff. But I don't know. I mean, I asked everybody if that 11 o'clock time would work for you on Monday, but I didn't hardly get any feedback from people. But
was that in the beginning of your class, or did you send out a notice? Sorry, I missed that somehow.
yeah, I just sent it out just recently, just because that's going to be like my online office hours for 10:10. I said I'd do Mondays and Wednesdays from 11 to 12, but hardly anybody responded. And I really, I mean, if some of you guys have classes at that time that you have to go to, that's what I wanted to know. Would it be better to do it later in the afternoon or something like that? I'm perfectly willing to change it to whatever works out best for you. So
for me personally, like I do have a class during that time, but I think for me right now it's just figuring out what times and what days is best to do my homework, because we're not really technically, like for my other classes, I'm not required to be on here, with my teacher. Do you know what I mean?
Yeah.
Sort of schedule.
Yeah, and see, that's what I don't know, how other classes are working it. So maybe what I'll do, I'll send out a little doodle survey, and it'll kind of just list some times that you guys can say which times are best for you. And if we want to change that time to something else, I'm totally cool with that. I just want to know what works best for you guys so that I can be available for you. And, and then you guys could work in kind of smaller groups and stuff during that time also. It would be a really good thing to do. Okay?
Thank you.
Yeah. All right, so let's look at this and see if everybody is good with how we came up with these. Remember, whenever we're putting these numbers in, right, when we're choosing our x-intercepts, our y is always 0. I mean, I was showing you on the other ones like how it works out, but it always came out to be 0. So I just want to make sure, I mean, it doesn't really need to take as long as maybe you're spending if you remember some of these things, right? And then on the vertex, right, I was putting -2 in place of my x there, but I did some of this kind of in my head. I did 2 times -2 was my -4 plus my 7, right? And then I put my -2 in the other parenthesis in place of x, so 2 times -2 is -4 plus 1, right? So I can combine those like terms and then multiply those together. I get -9. And similarly, right, that's the same thing that I did to find the y-intercept, right? 0 times anything is just 0, so 0 plus 7 in my first parenthesis, and then 0 plus 1 in my second parenthesis, right? And then just multiply those together. So when I graph this, well, first of all, where would my line of symmetry be? Can somebody just unmute yourself and tell me where would that line of symmetry be? There's
x equals -2.
Okay, and how did you know that's where it's at, x equals -2?
Because that's our vertex.
Yeah, that's the x-coordinate of your vertex, right? And so that's going to be the same thing here. All right, so if we plot these in here, let's see, so -3.5 and 0, let's see, that'd be 3, so I'm going to say 3.5 is about there, and then 0.5 is maybe about there, and then over -2 down 9, and over 0 up 7. Right. And so we can kind of see, so here's our axis of symmetry. I guess let me do it in a different color so it's clear. This isn't really part of the graph, but it helps us to be able to find out, right, all the symmetries that are there. So I know that there would be one kind of over here, also another point. And then it would look something kind of like this. Hopefully yours looks better. Just kind of always goes crazy looking. Hey, what questions do you have on that? Is that making sense?
Yeah, I have a quick question.
Yeah, of course.
I know it's too late for me to ask because we did everything else, but with our X, the graphing thing where we find our X, do we find our own points or do we get the points from the
So you mean like how are we coming up with these X's?
Yes.
Yeah, so we are picking them specifically. So like this -6, we're picking because it would make this factor 0. It's kind of like the opposite, right, of what's in there. So we're picking that. And then the same thing on the other, right, the x minus 2 factor, right, then we're picking the positive 2 because you see when I put, 2 in place of x there, that makes that whole factor go to 0. And that's what I'm trying to pick numbers that are going to actually make these go to 0. And then for the vertex, you're always picking your halfway point. So halfway in between the -6 and 2. So you just find the average, just add the -6 and 2 together and then divide it by 2. And that's how you come up with that next number. And then to find the y-intercept, it's always going to be 0 that you pick for your x. So yeah. Yeah, so I mean, I just want to help you see, like, there's certain parts of the parabola that are the most important to know, and so these are going to help you find those important parts of the parabola when you're graphing it. Does that make more sense?
Yeah.
Okay.
Makes sense. Thank you.
You're welcome. Thanks for asking. Okay, was there somebody else have a question?
Yeah, I do. On the homework, the 7.2 factoring the special cases, there's, with the one that you taught us today, this a plus b and a minus b, what if neither of them have a GCF?
So give me an example of one.
So 16n squared minus 9.
Down again. Say it one more time, sorry.
16n squared minus 9.
Okay. So you're looking for, so do you see that 16's a perfect square and that 9's a perfect square? Meaning, like, when you do, you're thinking what times what is 16? That's the same number. And that would be 4, right?
So you wouldn't need a GCF, you would just need to find a way to square both of them.
Exactly. So these don't have a GCF that will come out of both of them, but they are both perfect squares. So when you rewrite it, you'd put, and I'll just put it here so you can see what I mean, and then I'll just get rid of it. But that, so that 16n squared minus 9, that 16n squared, sorry, that squared went kind of crazy, is going to be written as, you want to write it as something squared minus something squared, right? And the something here would be what?
4n.
4n. Well, just 4n inside there, right? All squared. Do you see why it's 4n this way? Because I'm trying to think what times itself. So if I did 4n times 4n, that gives me what I started with, that 16n squared.
Okay.
Do you see what I mean? So that's what I'm trying to find here, is what number goes in here, what number would I multiply, well, in this one it has letters with it too, but what multiplied by itself is going to give me 16n squared. And then the same thing over here, what squared is going to give me 9.
Okay, that makes more sense. Thank you.
Okay, you're welcome. Thanks. Glad you asked. Those difference of squares and stuff are kind of crazy on there. And make sure you guys look and see, I did put more resources on our, Canvas modules and stuff. There are other videos and stuff that you can look at as well, to maybe help you on some of these things, because I know it's, you know, it's just different not being able to work with you guys in class on this. So I wanted to try and put as many resources as I could for you on there where you could use those. Okay. All right, let's see. Michael, you had a question too?
I'm sorry, no.
No? Okay, that's fine. Nikki, did you have one?
For the homework, the 7.2, like I think there's like 2 or 3 like worksheets or activities. Those are all part of just 7.2.
It is.
Right?
Yep.
Okay. There were some
Yep, so there's nothing on Edfinity that you're doing for 7.2. There's that, like, Who Wants to Be a Millionaire game, right, that you're doing, that kind of a thing. And remember, you can get extra credit on that one too. So you only have to get up to 32,000 to get points for this, but if you get up to 1 million, then you'll be able to get extra credit on it. And then, yeah, then there's going to be 2 other worksheets that you're just going to be working on. And like I said, you don't have to print these out like any of the worksheets that we're doing. You know, just, you can just work them out on paper and then just upload them like we have the other assignments and stuff. Okay?
Thank you.
Yeah. Okay, let's see. Natalia, did I answer your question or no? What are you asking?
You answered my question. I'm good.
You are? Okay, sorry. I sometimes don't see the chat until later and I feel bad. I'm like, I didn't see that. Okay, so let's look at this one really quick and then we'll go on to kind of the next stuff that we're going to be doing. But, so on this one, like whenever I have a leading coefficient, I always want to look and see if there is a greatest common factor that I can factor out of all of my terms. That is just going to make my factoring a lot easier. So remember that you always want to look for that greatest common factor first. Okay. I need to make a second. I need to make myself a note. I'm going to be putting something else on Canvas, and it's kind of like this factor flow chart, and I found that it helps a lot of students, and so I want to go over that with you, but and it's not something that you have to, you know, it's not an assignment or anything. It's just there to help you be able to kind of make sense of, you know, what you need to do, you know, as far as factoring goes, because I know some of you are looking at this going, oh my word, there is so much to factoring and it's kind of freaking me out, right? And so I want to make sure that you see that there is, let me see 1 second here. All right, so let me just bring this over here for a second so you can see what this is and what I'm going to have on there, so you'll know what I mean by this factor flow chart. So first of all, right, the very first thing that you're going to do at the very top here on this factor flow chart is factor out the GCF. So if there's any kind of GCF, right, greatest common factor of each of the different terms, you want to factor that out first. And then you're going to ask yourself, okay, what kind of polynomial do I have? Does it have 2 terms? Does it have 3 terms? Or does it have 4 terms? because depending on what kind of polynomial it is, you're going to go about, kind of factoring these in different ways. And this will kind of help you be able to know, okay, where am I going with this? So a lot of the things that we've been working with are these trinomials, the 3 terms. And so the first thing, right, it says is, are the A and C terms perfect squares? So I mean like that first and last term, right? Are those perfect squares? Kind of like the one that Rachel just asked about before. But it also has a middle term in it as well, okay? And if it is, then you could factor it with this perfect square trinomials. We talked a little bit about those last time, but I said usually students do just fine without this, because you can factor any trinomial using the way that we talked about, using the factor by grouping or doing the synthetic factoring. All right, so that's kind of helping you see where to go there. But if you have 4 terms, if it starts off with 4 terms in it, then for sure you're going to do that factor by grouping or box method. I'll go ahead and put box method in there too. I thought it was on this one. I have a different flow chart. Maybe I'll probably put that one up instead, but just so you can see how that goes. So if it's 4 terms, you're going to do factor by grouping, box method, like that. Okay, but if it has 2 terms, right, if it's a binomial and only has 2 terms, then it's either going to be, they're going to be perfect squares or perfect cubes. And so if it's a sum of perfect squares, right, so something squared plus something squared, we said that's prime, that can't ever be factored, right? But when it was a difference of squares, and that was the one specifically that Rachel was asking about last time, something squared minus something squared, then it always factors to be this way. All right, and then we talked about the sum of cubes and difference of cubes last time a little bit as well. So if you have something cubed plus something cubed, it factors to be this, and then something cubed minus something cubed factors to be this. So it's just to try and help organize all of the different things with the factoring, to hopefully help you see, like, have it all together in one place so you can kind of go, okay, what am I dealing with? Oh, I'm dealing with a binomial. Okay, I need to go down here. Am I dealing with perfect squares or perfect cubes? How am I dealing with that? Okay, and does everybody know what I mean by perfect squares and perfect cubes? Is that, like, raise your hand or ask if you're not quite sure what I mean by that. I think we wrote down some perfect squares last time, like 1, 4, 9, 16, 25. Those are all perfect squares. Perfect cubes would be like 1, 8, right? Because 2 cubed is 8. 3 cubed is 27, right? So those are perfect cubes. All right, so those are kind of what you're looking for on those. All right, and like I said, in next week I want to send out that doodle to everybody and figure out a time that's good for you, because I really want you guys to be able to still break out into groups and work with each other on it. It really is a lot more helpful if you can talk it over with somebody. You're going to remember it longer if you can explain it to somebody. You can help somebody else by explaining it to them too. So it's going to be a really good thing. All right, let's look at this one. So notice that on this one there is a leading coefficient of 3, and so the first thing that I want to think of there is their greatest common factor, right, on this? And I would start with 3, and I would say, can 3 divide into all of those terms? Right, actually, let me use a different one. Okay, and so then if you just on your calculator, figure that out. All right, so I'll be left with x squared on that first term. What's 36x divided by 3? Well, that will give us the 12x. All right, and then what's 105 divided by 3? I think it's 35. Okay, and then we need to factor it still further, right? All we did so far was take out the GCF. But now we need to look at this trinomial and factor that further, right? And so I'm thinking x times x is my x squared. What times what is 35? That adds to be 12. Right? And that will be 5 and 7. Right? 5 times 7 is 35. 5 plus 7 is 12. Right? Okay, and again, right, since this first number, that number out in front, it doesn't have an x next to it, right? So we're not going to be using that to help figure out where our x-intercepts are, just these factors, right, that have the x involved in them. So when we write this down, right, so we want to find out what x's are we going to pick for those x-intercepts, for the vertex, and for the y-intercept. Okay, and so for the x-intercept, I'd want a -5, because on this first parenthesis, right, if I put -5 in there, it's going to make that go to 0. And then on my second parenthesis, if I put -7 in there, that will make that go to 0. Okay. To find the vertex, remember, I'm just going to write halfway. Hopefully you remember what I mean by that, right? Halfway between these two. So if I'm doing -5 plus -7, all divided by 2, well, that's -12 divided by 2, which is -6. And some of you probably could have done that in your head, right? Because you're just trying to figure out what's smack dab in between -5 and -7. -6 would be there. And then to find the y-intercept, we're always choosing 0 to be our x. And then let's just continue this to figure out, remember, the whole reason why we picked this -5 is that because it makes one of those terms 0, and 0 times anything is 0. So that automatically, like I know my x-intercept, my y is 0, and this is my x. Okay? And then if I put -6 in there, right, so I've got 3 times -6 plus 5, I'm just putting it into this factored form, and then -6 plus 7, so I've got 3 times -1 times 1, so that's just going to be -3. Right, so there is my vertex, or my turnaround point there. Right, and then when I put 0 in, right, then I'm actually always going to end up with this number, and I think I talked about this last time, but I can't remember, and if I did, it may have been kind of like in passing, but when in this first form that we have it in, this standard form, right, think about if I put 0 in place of x in these, well, I get 3 times 0 squared, that's just going to be 0. 36 times 0, that's just 0. And so it always just leaves me with whatever that last number is there. And so that would be 105. So that's going to be this one, which that's going to go off the grid there, so we're not even going to be able to get to that part, right? But that's where it would be if we could have it there. So let's just graph these other 3 points. So I've got, here is my -5, 0, here's my -7, 0, and then my vertex is over -6 down 3, which is maybe about here, because these are moving by tens on the y-axis, so it's not very far over there. And then, you know, like I said, the y-intercept is going to be clear up here and over, so we just know that it's going to be something kind of like this. Ooh. Oh my heavens. Sometimes. All right. Gotta get better at these. That'll take some practice. All right, and where would our axis of symmetry be? Can somebody tell us?
-6.
Yeah, So but the name of it is, the line is x equals -6, right? So, because unlike the labs and, you know, quizzes and stuff like that, it's going to ask for that axis of symmetry. So make sure you're writing it, it's that line. So make sure you write it as x equals 6. Okay, right there. All right, so that's kind of, you know, just graphing these quadratics. And just keep in mind that these quadratics are always going to have that same shape. They're like a U-shaped graph, and so they're either a right side up U-shaped graph or an upside down U-shaped graph. And so, but they're always going to have that same shape to them. We're not going to talk about it if like the parabola is laying on its side. We're not going to deal with those because those aren't functions, and we're just trying to deal with functions. But you'll talk about those in other classes, in 1050 specifically, if you're going on to that class after this one. Okay. All right, and I'm going to skip over a few pages, and I want to skip over until you get this one. So in my book it's saying 119, but I can't remember if mine is exactly the same as yours. So look, it should be somewhere around 119. It says question 8.2. All right, so these are 3 different functions, okay? And remember when we talked about linear functions, we said if it was adding or subtracting by the same number every time, then we could tell it was going to be linear. If it was being multiplied or divided by a number every time, then we could tell that it was going to be exponential, right? But now we're going to talk about, well, what does our graph look like? What kind of a pattern do we see happening when we have quadratics also? Okay, so let's look at this first one. All right, so notice our x's are just increasing by 1 every time, which is good. But what is happening on our f of x? So if I'm moving from 3 to 7, right, and if I was thinking, you know, like it's being added, you know, if I take 3 plus 4, I get 7. And then let's keep that going down here. Well, 7 plus what gives me 13? Well, that would be 6. Right? And then 13 plus what gives me 21, which would be 8. 13 plus 8 is 21. All right, and then let's see here. Down a little bit more here, and then the last one, 21 plus what gives me 31, and that would be 10. So I'm looking at this going, okay, well that does not follow any of the patterns that we've talked about so far, because it's not increasing by, like, it's not adding 4 each time, or it's not subtracting 4 each time, or it's not being multiplied by 4 each time, right? But we do see it looks like there is a pattern that's happening there, right? And so what we're going to do on this is, if we can see there's kind of a pattern happening, we want to look at what's called the second difference. And so let me write this in a different color so you can see. So the first difference, right, from here to here, it was increasing by 4, but now I want to look from here to here. So if I look at this from 4 to 6, right, if I add 2, 4 plus 2 gives me 6. From here to here, 6 plus 2 gives me 8, and 8 plus 2 gives me 10. So on this one, right, the first difference, right, wasn't the same, but my second difference is constant. So let me write that down here. So we're going to say the second difference is constant. And when that's the case, that means that it is a quadratic. right? This is the pattern that we're looking for when we're trying to decide if, if we're given a table of values, is this linear, is it, exponential, or is it quadratic? Okay, and so this one is quadratic. I'm going to just write that out over here. Okay, because the second difference, that's the thing that's telling me it's quadratic, because the second difference is constant. Okay, let's look at these other graphs here. So what about here? So if I go from 10 to 13, right, say, okay, if I add 3, that will get me there. Add 3, it gets me to my next number. Add 3, and add 3. All right, so this one, my first common difference, is the same, right? And so what kind of function would this be then?
Is it linear?
Yeah, it's linear. So whenever you're adding or subtracting by that same number, right, on that first difference, then it's linear. Okay, and then what about here on this one? Right, so going from 27 to 9, 9 to 3, 3 to 1, 1 to 1/3. You may see what pattern's happening there.
Is it dividing by 3?
Yeah, it's dividing by 3, right? If I do 27 divided by 3, that gives me 9. Right? Divide that by 3, I get 3. Divide by 3 again, I get 1. And divide by 3 again, I get 1/3. Right? So what kind of function would this be if we're dividing by that same number each time? So if you're multiplying or dividing, right, by that same, if it's a constant, we called it a common ratio before. So this would be exponential. Okay, and usually we talk about it in terms, instead of division, we talk about it in terms of multiplication. So remember, that's the same thing. Dividing by 3 is the same as multiplying by 1/3. Right? So if I said 27 times 1/3, that would still give me 9. Right? So usually we think about it, as multiplication, but it's the same thing, as long as you understand that. So I want to make sure there. Okay? And that's how you can tell, it's quadratic, linear, and exponential. Okay? And so on part A, we kind of already talked about this, but which one of the three functions is a linear function, and how do we know? Well, it's that middle one, right? That g of x.
As a constant rate of change.
Yeah. Okay. Oops, didn't want to put equals. Because it has a constant rate of change. Right? Meaning that you're adding or subtracting, right, each time. Right? And then on part B, okay, which one of the three is an exponential function, and how did you know? So that was h of x, and how can we tell on that one? It has a common ratio, right? But we also talked about that as a percent change, a constant percent change, which would mean the same thing there. Whoops, what am I doing? So even though this isn't written as a percent, right? If you had, I mean, 1/3 isn't the best one to use because, if you're doing, 1 divided by 3, that's 0.333333. So it's about a 33% change, right? So that's what we're talking about there. You can take any of these common ratios and make them into a percent. And so a lot of the story problems we dealt with were percent change, right? All right. And so then somebody tell me in your own words, because I want to write this down in the punchline, how can you tell if a function is quadratic? We're going to do that. How can we tell if function is quadratic given a table of values? What did we say would happen there in this table of values?
If the second difference is a constant.
Yeah, so you'll kind of do that first difference and you'll look at it and go, okay, that's not the same every time, but I see a pattern that's still happening there. So that should clue you into, okay, let me try that second difference and see if I come up with something that's constant, right? So, because we need to have a constant second difference. And this second difference, it's kind of cool, is referring to, it actually is the acceleration. It's dealing with constant acceleration. Right, so maybe like if you threw a rock over a cliff, right, and the gravitational pull is going to be pulling it down, and that would be a constant acceleration. It would be, increasing that way. And that's kind of what happens. I mean, so I want to I'll just make a little cute little picture over here, right, to help you see what I mean. So say that this is my cliff, right, that I'm going over, and maybe there's some water or something down here at the bottom. Whoops, I didn't want that to be. Okay. Why is it doing that? All right, so if I wanted, so we were throwing a rock over into the water. Well, when we do that, right, it doesn't go down in a linear form, right? Goodness, I'm just gonna scream here. I don't know why it keeps doing it so weird. So you would throw the rock up in the air and then down it would come, right? And so it's making this parabolic shape, right? It's not all of the parabola. Maybe if you, used a cannon, shot something in the air, and then it would come down. Even if you shoot like a bow or an arrow or a gun, right, it still has kind of that parabolic shape to it. It doesn't just go straight. And so that is what's kind of important to remember there. And that constant difference, like I said, is dealing with constant acceleration. So when we're talking about some story problems with this, I want you to see how that acceleration is involved with this. Okay, all right, flip the page over to the next one. Let's look here. All right, so first thing that we're going to do is we're going to fill in the table. So we want to know, when x is 1, 2, 3, 4, 5, and then we're going to look at it and decide if it is linear or exponential, or if it's neither of those, if it's, maybe it's going to be quadratic. So we're going to kind of see that. But to fill in this chart, right, we could just, so when we have 1, we put that in place of x there. So 1 squared plus 1 plus 1, well, that's going to give us 3. Right. And then if I keep going and I put 2 in place there, so 2 squared plus 2 plus 1, well, that's going to be 4 plus 2 plus 1. So that gives me 7. Right. And then I keep going. Right, now I'm going to put 3 in there. So 3 squared plus 3 plus 1. So it's going to be 9 plus 3 plus 1. That's 12, so that's 13. Right. And then let's do 4 squared plus 4 plus 1, right? I'm just putting x in place, or putting 4 in place of my x there. So 16 plus 4 plus 1, so 20 plus 1, so 21. All right, and then the last one, we can keep going on that and do that, but let's look here, right? So do you see that this kind of relates to one of the ones that we just talked about on the other page, right? How, so we're going here, all right, here we're going up by 4, here adding 6, and then the next one adding 8. Right? And so it's not linear, it's not exponential because it doesn't follow those, but I do see that there's some kind of a pattern that seems to be happening there. And so if I go further, I'm thinking, okay, yep, I can see that my second difference is going to be the common one here, right? And so that's kind of what I want to help you see. So we found these table of values, right? But this is the quadratic equation, right, that goes with that table of values that we just dealt with on that last page. So when we have something like this 3, what was that, 3, 7, 13, 21, 31, right, when I'm looking at that, this is going to be the quadratic equation that goes along with this. Okay. All right, so I think we've got that down a little bit. So it's always the second difference that we're looking at, a common second difference there. Okay. Let's go over to the next page, and here we have a little story problem, right, that we're going to be talking about here. And I want to look at. So the tallest building in Salt Lake City is the Wells Fargo Center. It's 416 feet tall. Right? If you drop a 2-pound rock from the top of the Wells Fargo Center, how long will it take to hit the ground? Okay. So what do you guys think? Do you think it matters how much it weighs? Do you think that 2-pound rock, so if you put a 2-pound rock over the side, or you did like a penny or something like that, is that going to affect the the amount of time it takes to hit the ground? What do you guys think?
Can you repeat that question again, please?
Yeah, just said so does it matter? It's telling you drop a 2-pound rock, and I'm not saying anybody should do this. Do not go to the top of the Wells Fargo building and drop a 2-pound rock off of it, right? But if you dropped a 2-pound rock off the top and you were trying to figure out the time it took, or if you took like a quarter and you dropped it off of the top of the Wells Fargo building, will that change in weight affect the amount of time it's going to take to hit the ground?
No, because gravity affects it all things the same.
Yeah, thank you. How are you feeling, Joe?
Just swell.
Just swell, okay. I'm glad you're here. Yeah, so it doesn't matter. The Earth's gravitational pull is always going to be the same. And so that's when we're looking at our equation here underneath. So you're not going to have to figure out this equation. They're going to give this to you. But that negative 16, that part of this equation, is the Earth's gravitational pull. Okay, and then you can see that that 416 deals with, well, that's how tall the building was, right? So all we're dealing with here is what the height of the building is and the Earth's gravitational pull. And I just say the Earth's because remember, gravity is different. Like if you were on the moon or something like that, it would have a different gravitational pull than what the Earth does. But since we live on Earth, we will use the Earth's gravitational pull. Okay. All right. So let's. So what I want you to look at here, and we're going to be. I want you to make a little chart, a little table of values. Okay. And you're going to be. We're going to. You know, choosing some t's and figuring out what the h of t is here. And I want you to just start off with t equals 0, and then let's just go up from there. So do, you know, t equals 0, t equals 1, t equals 2, 3, and then maybe go to, actually I want you to kind of go up through 6. So let me give you a little bit of time to do this. And you can just use your calculators too to figure this out with. Get those out. All right, so like on the first one, you're going to put 0 in place of your t. So you're really just doing what's 416 minus 16 times 0 squared, right? And so all of that's going to go to 0. So we'll just have, that's going to be 416. Okay, so now do the same thing, but now in place of the 0, put 1 instead, and 2 and 3. Okay, and figure out what all of these are going to be. Just use your calculator. I want it to go kind of quick. Just plugging those in. Okay, when you have all of these answers for these up through where t equals 6, go ahead and raise your hand. Just stop there for a second. Just figure out what the numbers are. Click your hand raise button on there when you have those figured out. All right, Braxton, what did you get for t equals 1?
I got 400.
Yeah. Okay, Haley, what did you get for t equals 2?
I got 352.
Awesome. Okay, 352. Lexi, what did you get for t equals 3? 272. Okay, how about t equals 4? Lily, do you have that one?
I got 160.
Okay, 160. And then what else? Let's see, Joe, do you have for t equals 5?
16.
16. Okay, and then t equals 6. You should have gotten a negative number on it, and I want to talk a little bit about that. So you should have gotten negative 160, right? If you got there. Okay, so these are the numbers that you should have. And notice it's starting off, right? This is the height of the building, and then the height of the building is decreasing. So this is as the rock is falling down, right? At 1 second, because this is talking about time. Right, so at 1 second, it's still 400 feet in the air. At 2 seconds, it's this far in the air. But at 6 seconds, it's saying it's negative 160 feet in the air. So unless that rock, you know, was like an asteroid or something and was able to, you know, pierce through, the soil or the asphalt or something like that, right? This doesn't really make sense. Usually it would just hit the ground, okay? So I want you to kind of think of that and keep in mind. So when, this h of t, this is our height of the rock, right? So when the height is 0, right, that's when it's hitting the ground, okay? All right, so we'll come back to that in just a second. But let's answer the question that was asked here then. So it wants to know the second difference for the function. So that means that you need to first of all figure out what the first difference is, right? So you're going to be just figuring out, what number is being subtracted here on these. Let's see. All right, so on this one, it's negative 16, because remember, you're going down 16, right? So you're doing 400 minus 416 when you're figuring these out, right? And then the next one would be negative 48, okay? But somebody tell me what the next one's going to be here, right? So you're doing 272 minus 352, right? Got to subtract them in that order. Whenever somebody has that one, just unmute yourself and tell me what you came up with. So that's 272 minus 352.
Negative 80.
Okay, negative 80. And then if we go do this again, right, in your calculators, you're just doing 160 minus 272. Right, subtracting these guys now. It should be negative 112. All right, I'm going to stop right there because this next one's going to be a little bit different because it goes below 0. So let's just stop there, and this should be enough to be able to help us figure out what that second difference is now, right? Oh, great. It's acting up again. Okay, so if I go from here to, so negative 16 to negative 48, right? What would that second difference be? Anybody? So in your calculator, remember you're going to be doing negative 48 minus a negative 16, because you're doing that. Doing your negative 48 first, minus that top number. What do you get there?
Negative 32.
Yeah, negative 32. And then keep doing that. So now do the other one. So now do negative 80 minus negative 48. And what do you get there?
Negative 32.
Negative 32 again, right? And then if we try it one more time, that negative 112, or yeah, negative 112 minus negative 80, you should still get another negative 32. And this is freaking out again like it did last time. I don't know why it does that. It's not letting me write on here anymore. But so on here, make sure you're writing down next to it, showing that that second difference is the negative 32. Okay. Okay. And so that is its constant acceleration, right? So, and so since it has that common difference, like the second difference is constant, then we can tell that this is going to be a parabola. And you can kind of tell, you know, like from that other picture that I drew up here before when I was saying, you know, something. Oh, okay, never mind. It really is freaking out on me now. You guys see that? Oh, lovely. Okay. Well, I think what this is saying is we're probably done for the day. So, but I mean, that's really where I wanted to get into. But I did want to, you know, have you guys figure out, and so maybe I'll just leave this for you to think about, and then we'll start there next time. But I want you to think about how long will it take the rock to hit the ground. So the question right underneath there, so part B, right? So how long will it take the rock to hit the ground? So we're trying to figure out when h of t is 0. And if you look at your chart again, you can tell it's going to be somewhere between 5 and 6 seconds, right? Because it goes from 16, to negative 160. And so we can tell 0 is going to be somewhere in between there. Okay.